Welcome to the second video of this basic introduction to index notation in the context of linear algebra. We're going to talk today about the notion of covariance, contravariance, change of basis, and the beginning to the notion of tensor, even though we will introduce that properly as we advance in the course. All right. Now imagine that I have a vector space of dimension n, and I have two bases made of vectors that span the whole space, right? Any vector in the space. So I have the bases without primes and the bases with prime e1, e2, e3, en, e1 prime, e2 prime, all the way to en prime. Now, when you have two bases, there's a change of basis, some linear operation that maps elements of one basis to elements of the other basis. So for example, this is an example. Imagine that I have one basis that is what we usually call the canonical basis. I represent as 1, 0, 0, 1. And again, I write an equal sign. It's a bit of an abuse because those are abstract vectors and those representations in the canonical basis, actually, of all of them. So you know that there's a matrix, right, that maps one into the other. These two are bases. In fact, they're orthonormal bases. And you can tell that this matrix here, let me call this matrix lambda, for example, even though in algebra you probably call it P a lot, or even P minus 1, depending on the convention that you use. This change of basis matrix maps. So I made here, what did I do? I made a vector whose components are actually the vectors of the bases. And then I can write a matrix that maps the vectors of the all bases into vectors of the new bases. And you can check that this operation precisely maps these vectors into these ones. All right, according to this. Right, in general, I mean, we can write in index notation, we can make the following. We can talk about this object, we can get look at that. This thing that has an index down is, let me write Greek indices just for fun. E mu, this is the muth vector of the all bases, and that gets mapped through some linear operation, and this linear operation is gonna contract that index mu and return an index nu. Okay, and then this is going to be the new element of the basis, sub nu. So you say this is the same as this. So is the component nu, the nuth component of this vector, is actually equal to the entries of the matrix, right, acting on the vectors of the basis, okay? I want you to understand what this is, this object, as opposed to when we write v mu for a vector, these are the components of the vector. Varying the index mu here are the number of elements in the basis. Every e mu, like e1, is not a component, it's a full vector, it's an element of the basis, okay? And we write the index downstairs for a reason that we will learn in a second. Hope that's clear. So this is the change of basis. Given two bases, there's always a linear operation that maps one basis into the other. All right? Cool. Now the question that we can ask is, let me ask one question for you. How does a vector v transform under change of basis? So if I have v, and this vector v, I can write, of course, as some components v mu, e mu, right? Is that, right? In the old basis, it's components without prime, v mu, e mu, right? A vector can be written as a sum of the elements of the basis with some proportionality constant, as a linear combination of elements of the basis. Now, what happens if I change basis now? What happens to the vector v? And the answer is nothing. The change of basis does nothing to the vector. Let me put it graphically. There's an arrow here, and I change basis by rotating my head. It's the same arrow. The components change because my axis, the vectors in the direction of the axis, for me, have changed. So what happens on the changes of basis is that the elements of the basis change, and of course the components of the vectors change, but not the vector itself. And again, if you are confused by that, is good, because being confused by that kind of contrasts this concept that I'm trying to hammer in, which is, do not confuse a vector with its representation in a basis, okay? The vector is an abstract object. Now, I didn't write an arrow, I should have written an arrow. A vector is the abstract object, and you can take the components as the representation of the vector in a given basis. But if I change basis, it's the same vector, now expressed in components in a different basis. So for sure, if I write in a different basis, it's the same vector. The only difference now is that the components are going to be primed and the vectors are going to be the new vectors, the prime vectors, the vectors of the new basis. Now, the question that I have for you, what we're going to deal with right now, is if the elements of the basis transform with this matrix lambda, this matrix of change of basis, how do the components transform? That's what we're going to figure out now, and that's going to give us a definition of covariance and contravariance. All right. Before we set out to do that, let's summarize the point. If I change basis, I'm mapping some vectors to some basis of vectors of the space into a new set that spans the whole space, a new set of vectors of the space. And of course, if I have a vector v and I change basis, but that doesn't do anything to the vector v, but it does something to the components of the vector v, because now you're expressing that vector in a different basis. So I can write v either way as a combination of elements of the original basis or as a different combination of elements of the new basis. Okay? That clear? Hopefully yes. If not, please do ask questions. Now, let's see. If I know that these two things are equal, oh, by the way, notice the following. I could write here a nu if I want, and it's the same, it changed nothing. If I write different indices, because this is a dummy index, again, it's a sum, it changes nothing, okay? So we can keep it as mu, or we can keep it as nu, as we want. It's the same thing. All right, so let's compute how, so again, what we're going to compute is knowing this, I want to know this. So I want now to find a matrix, what do we call it, Q for question? Yeah, let's call it Q. So I know now that the V mu primes are going to be different from the V mu. So I want to find out the matrix Q that takes, maybe I'll call it nu, just to use the same, it doesn't matter, right? But just to be a bit more aesthetically pleasing, nu and then mu, V mu. So basically, I want to find this Q. What is this Q? What is this Q that maps the components in the old basis to the component to the new one, given that I know lambda? So our starting assumption is that I know what lambda is. This is the change of basis. Somebody tells me this is a basis, and this is the new basis. This is how they relate. How do the components change? Let's find out, and we're gonna find out with index notation. All right? In let's say in Rn. Okay, as we're doing here. Wonderful. So let's find this Q, shall we? How do we find this Q? All right, so I'm going to try to operate with my amazing /s, right? Handwriting. Okay, so what we're going to do is we're going to write this equation. So the left-hand side, I'm going to write again. So V vector equals V mu E mu. And now I'm going to write this, but I'm going to substitute, these expressions here. Okay, so just to be aesthetically pleasing, I don't need to do that, it's all correct, but to be aesthetically pleasing, I'm going to rename this nu as mu, just to make it easier for you the first time, and then nu as mu. So that does nothing, because those are indices, like calling them Joshua, but I'm going to do a swap, okay? Let's do it. Okay? And this is the same equation, I haven't changed anything, just the names I gave to the indices, which is my choice, right? Anyway, let me substitute V prime mu. So V prime mu would be Q mu nu V nu, of course, this is V prime mu. And then I'm going to substitute E prime mu. So from this equation, E prime mu would be lambda mu. Now, I might be tempted to just copy this, but you should not. Why? Because this dummy index nu is already used. You should not repeat. It will be correct if you do it right, but it's unlikely to do it right. So let me give you this rule for index notation. Do not repeat dummy indices. If you already use a dummy index for something, don't use the same, because you will make a mistake if you don't have a sum index there, a sum symbol there. So use a different one. For example, I'm going to use sigma, just for fun. Sigma E sigma. All right, and this thing is E prime mu. Okay? So all that I did is substitute these two expressions for this one and for this one. Wonderful. So the next thing I'm going to do the next step. So we take the next step, and the next step, the left-hand side, I leave the same. And what I'm going to do is I'm going to reshuffle these terms. Remember, those are numbers. There's no, oh, but you can't move because it's a multiplication. No. Those are numbers. Those are sums of numbers, all right? So I can move them around, and I'm going to put first v nu. I mean, I say numbers even though this is a vector, but you know what I mean, hopefully. V nu is sigma. And then I have, let's write like that, lambda mu sigma q mu nu. And then we look at that and realize, this is almost a matrix multiplication. The only thing is that for it to be a matrix multiplication, then it has to be, for it should be the second index of the first one contracted with the first index of the second. But we already did some practice on that. So we know that if I transpose lambda, so I'm going to do nothing here, transpose twice if you want. So v nu is sigma, that's the same thing. But I'm going to do now lambda transpose and then swap the indices, sigma mu q mu nu. Wonderful. All right. So what I have here is that this matrix here, right, is a matrix multiplication. All right, wonderful. So let's just write this equation again. So we're going to have here now in this step, I'm going to keep this as is, E mu, and this is V nu is sigma. And then let's call this matrix something. Let's call it, I don't know, maybe W. There would be a matrix W. That matrix W with entries sigma nu. And that matrix W is, of course, the entries of the product, lambda transpose Q entry sigma nu. So that would be W sigma nu. And this is the definition. All right, so I need these two things to be equal because they're equal. We started from the equality, right? So the question is, what should W be for these two things to be equal? Well, the only way they're going to be equal is if these things, I need this to be a sum over V and E with the same indices, not different. So it should be a matrix that has all the entries 0 and one's in the diagonal, you see? Because I could, if I wanted, I could call this nu, this is a dummy index on the left-hand side, just for aesthetics. And you see that if I have here, if this thing were the delta sigma nu, then that would be true, right? If this thing is delta, the two things will be true because that means delta in a sum, delta, this is a Kronecker delta, which is also what we call the identity. Why? Because this is the Kronecker delta, sigma nu, if you define it as is 1 for sigma equals nu and 0 for sigma different from nu, that's exactly the entries, the matrix elements of the identity. Notice that in here, I don't respect which index goes first. For the identity, it's going to be the only matrix where I'm going to write the indices one on top of the other. Okay? And I do it on purpose for a reason. And we will discuss that more when we learn a little bit more. Okay? But for now, you see that if this thing is the delta, then the two things are equal. So this equation implies that W sigma nu has to be equal to delta nu sigma, or sigma nu. Has to be the identity. Because if true, right, if it's true, then you would get this equal to, so let me just erase that, and we say, if it's true, right, what happens, taking a step here, would be V nu is sigma delta sigma nu, and then you do the sum over sigma, the substitute, the delta substitutes in a sum, you remember, right, that if you have WAB delta BC, the sum over B gives me WAC, right? That's what the delta does, kills in the sum all the entries that are not equal, B and C. So this thing would be equal to B nu, E nu, right? Or alternatively sigma sigma, it doesn't matter, but it gives you the same result, okay? Left and right. So that needs to be the delta, that needs to be the identity. But that allows us to solve for Q. So that means that lambda transpose tensor product with Q has to be the identity. All right, so we know what Q is. Q has to be the matrix that is the inverse of lambda transpose. So it's lambda transpose minus 1. Or if you want, which is the same, lambda minus 1 transpose. It's the same thing. All right, so because change of bases are invertible, so the inverse always exists. All right. So, wonderful. We found that if the elements of the basis transform with a change of basis matrix lambda, now the components of the vectors transform with a matrix Q, which happens to be the inverse transpose of lambda. All right? So let me summarize this result. So instead of Q, which was kind of cool when it was an unknown, let me call it lambda tilde, which is the standard notation. So if the elements of the basis transform with the matrix lambda and the change of basis, then the components of the vector transform with the matrix lambda tilde, which happens to be the inverse transpose of lambda. All right, so this is interesting because we found that the elements of the basis transform in a particular way and the change of basis, which is a change of basis, is precisely saying how the new basis is defined in terms of the old one, okay? Then we find that the components of the vector transform with something different, which is with the inverse transpose of lambda. All right, so that will allow us to define the notion of covariance and contravariance. Let me quickly write it on the board and let's read it together with a little bit of this crappy editing magic, as I call it. Okay, so here's a first definition. Objects that transform under a change of basis, like elements of the basis, that is with lambda, remember that the elements of the basis nu are lambda, nu mu e mu with a prime here. So if it transforms on the change of basis with lambda, with one lambda, we said it's one time covariant. And then the components of covariant objects have subindices. Again, the covariant object here is the vector whose entries are elements of the basis, if you want, okay? So things that transform, like the collection of elements of the basis with lambda, will always have index downstairs, and we call those covariant, okay? Or one-time covariant if it's only one index. Now, objects that transform and the change of basis, like the components of vectors, not like the elements of the basis, and that is with lambda tilde. And remember that lambda tilde, let me write it here. So V nu would be lambda tilde, and that would be nu mu V, without a vector, of course, sorry, my bad. Mu, where lambda tilde, of course, lambda tilde, let me remind you, is the inverse transpose of lambda, okay? So objects that transform with lambda tilde, that is like components of vectors, are what we call contravariant. And the components of contravariant objects have superindices. Now, of course, we wrote matrices before that have one index up and one index down, like one-time covariant, one-time contravariant. So what is that? Well, to understand what it is, let me introduce a couple more notions in the context of linear algebra. These notions will be expanded a lot when we see differential geometry, but as an introduction, let's talk about the dual basis, and I'm going to relate it a little bit with things that you've seen in your quantum courses. All right, let's see. All right, so several notational and conceptual jumps here. Now, notice the first thing that I'm not going to write arrows anymore in this course unless I am talking about relativity and spatial vectors. Now, I'm going to change the arrows for vectors because we're generalizing notions and that notation of the arrow is a bit obsolete for what we're going to do. I'm going to denote vectors with sharifa, right? So you see that I add a little sharifa. In the notes, vectors are going to be sharifa, character, like serif kind of character, okay? But then you see this is a sharifa. So this is an E that I added a sharifa to it. So that's the sharifa, okay? So if it were a vector V, I would add the sharifa like that. Okay, so that would be the equivalent of writing the arrow on the board. But I'm no longer going to write the arrow. But you know that these are vectors, huh? They have serifa, they are vectors. So I'm going to define the notion of the dual basis to a basis of a vector space V. So in mind that I have B being a basis of the vector space V, n-dimensional vector space. Now the dual basis B star, dual to B, is a collection of linear operators, look, that I write with elements with serifa, but now the indices are upstairs, okay? Such that the action of those operators on the vectors of the basis give me the identity, give me the Kronecker delta, all right? Now, an example of that, if I give you R2 and I write, let's say column vectors 1, 0, and 0, 1, then you say, okay, what are the operators that give me that delta? Well, if this is E1, again, this is a representation of E1, and this is a representation of E2. Then I know that if I write E1 upstairs as now a column vector 1, 0, and then E2 as a column vector 0, 1. All right, with a disclaimer that certainly index upstairs or downstairs do not mean rows versus columns. It is true that if I represent the elements of the basis, you see, the elements of the basis, say it's R2, I represent the elements of the basis with column vectors. I can define linear operators, matrices. In this case, this is a 1 times 2, but this is a 2 times 1. These matrices, E super 1 and E super 2, which are the rows associated with these columns, happen that, okay, what is E1 acting on E1? Okay, so I have 1, 0 acting on 1, 0. This is 1. What is E2 acting on E1? All right, that is 0, 1 acting on 1, 0. That is 0. All right, what is E2? E1 acting on E2. All right, that is 1, 0 acting on 0, 1, which is 0. This matrix product, right? That's what I'm doing. It's a linear operator acting on a vector. And I write E2 acting on E2. That gives me 0, 1 acting on 0, 1, which is 1. And if you see, this is exactly the Kronecker delta. When the two the two indices are the same, I get a 1. When the two indices are different, I get a 0. So if this is a representation of the basis of V, this is a representation of, this is a representation of the basis of V, this is a representation of the basis of V star, or B star, which is the basis, right? So the dual basis is made of the operators that acting on the elements of the basis give you the identity. But of course, if this thing spans a vector space, which is R2, this also spans a vector space, which is R2 as well. But you see, they form a vector space, and this space is the dual. And even though it seems that it's the same space, as in it's R2 in a way, they're different, because the rows and the columns here that I used to represent are different. They capture different structures. If these are the vectors, these are matrices, these are operators on the vectors. All right, we can define elements of the dual space. Let me call them, for example, omega, and again, no arrows. An element of the dual space will also be spanned by the basis of the dual space, right? So I can write omega 1 E1 plus omega 2 E2, etc. Omega n En. But I can just write in Einstein notation as omega mu E mu, right? So this object, omega, is an element of the dual space to V. So it's an element of V star. That thing is an element of V star. Now I can get V, which is V1 E1 plus Vn En, which in index notation would be V mu E mu, is an element of V. So you see, I have an element of the dual space, a vector of the dual space if you want, oftentimes called covectors. So let me call this thing a covector. And let me call this thing a vector. This is a physicist way of calling things. Mathematicians would just roll your eyes at you if you start calling them that. But it's fine, let's call them that because we are mostly physicists. I'm definitely a physicist. My apologies to, in fact, during this course I may trample sometimes some things the mathematicians may be mad. They have my full respect. I think they're right and they should totally tell us how to do things. But I'm going to trample some things, and I think it's okay to do it as long as you know that you're doing it. So anyway, the typical notation for this, we call this vectors, and the elements of the dual space, we call them covectors. Okay, the elements of the vector space vectors, the elements of the dual space covectors. And of course, we can compute now a contraction between a vector and a covector. All right, so the same way that I have the action of elements of the dual basis on element of the basis, I can define the action. Maybe let me conveniently define this notation as EI acting on EJ, like that, with this bracket, because that's the usual notation. I can do the same here. I can do what is omega, which is an element of the dual space, a covector, acting on the vector V. So what is this? Well, I can use the linearity to, right, well, let's just first expand this in components. So that would be omega mu E mu acting on V mu nu, let's call it nu, E nu, right? And then these are numbers and these are vectors, and only vectors are on vectors, so I can take the numbers out. This is a bilinear operation. So omega mu V nu, and this would be E, I took the numbers out and I left the vectors in, mu nu. And of course this thing is a delta, so this is delta mu nu, all right, and because it's a delta, this becomes omega mu V mu. All right, so the sum of components, 1 to 1. So you see, we have the action of the contraction. That probably reminds you of something like an inner product at the level that you see this. But no, we're talking about different structures as we see, but that can help you make sense of it, I think. Anyway, so the elements, just keep in mind that we don't have an inner product defined here yet. I just defined the dual space by defining the dual basis and see what it spans. And because I know the action of the dual basis on the basis of V, I can compute the action of any element of the dual space on any element of the vector space. The action of any covector on a vector. And that's what we call a contraction. Which basically reduces to, right, just take the components in the basis of one and the dual basis to that one for the covectors, and just multiply 1 to 1 and sum all the components. All right, wonderful. So now that we know that, we understand. By the way, what does that remind you of? It should remind you of the quantum courses you saw. Because in quantum courses you have cats and you have brass. And what are brass? Brass take cats and return real numbers, right? What are covectors? Well, they take vectors and return real numbers. This contraction is a real number, right? This is a sum of numbers, a sum of components. This is literally the same as you do in quantum when you consider the space of brass versus the space of cats. If the space of cat is the vector space, then the space of brass is the dual to that. Now in quantum you have an inner product, and you have norms that come from that inner product. You work with Hilbert spaces, so a little bit more structure than so far. As we will be introducing more structures, don't worry, we will discuss that. We will discuss metrics and inner products, but not yet, not quite right now. I'll give you an introduction a little bit in a second, but we will see it better when we see block 2, okay? But then again, this is literally analogous. It's the same thing that you do when in Dirac notation, you take cats and brass, okay? Dirac notation is just a handy way of doing it when you don't have to deal with things that are too complicated. And in quantum, the structures that you use in terms of linear algebra don't tend to be that complicated, okay? Anyway, so, wonderful. We've seen the notion of dual basis and dual space. And, very interesting. Look at the components of an element of the dual space. The components have indices downstairs. And the index downstairs is not just by coincidence. In order to get the identity, you need to have upstairs and downstairs, so that the basis of elements of the dual space have index up, and therefore, because of Einstein convention, is telling you that the consistent way of writing it is the components with the index down for omega. But that's not a coincidence. The notation is actually capturing the algebraic structure of it. The entries, the components of a covector are covariant objects. They transform with lambda. So very important. So if the components of let's say V mu, these things, V mu prime, is gonna be lambda tilde mu nu v nu, then we know that the elements of the dual vector space omega mu prime are going to transform with lambda, same as in the case of the elements of the basis. So we say that the dual vectors, the covectors, are covariant. They have one covariant index. The components have one covariant index as opposed to the components of vectors that have a contravariant index. All right? So a covector is a covariant object, we say. Whereas a vector is a contravariant object. All right. Let's go one step beyond and talk about linear operators, all right? And see what they are and what they do. And with that, multilinear operators, we're going to define tensors. And that's the second last thing I'm going to do in this video. Let's do it. All right, let's consider a bilinear operator, A, that takes one vector and one covector, one element of a vector space and one element of its dual space, and returns a real number. What kind of object is that? Well, you can think of it as in a representation as a matrix. Say that a matrix takes one object, V1, V2, from V, and one object, omega 1, omega 2, from the dual, right? And it returns a real number. That thing is a number, right? When you do this matrix product, you get a number. So you can take the components, you can see that this object, this object A, has matrix elements A, mu, nu.
All right, I just wrote something slightly inconsistent between the matrix elements that I wrote and the representation of the components of the matrix that I wrote. The matrix elements that I wrote are the equivalent to the second line in this screen capture. As you can tell, for the second line in this screen capture, the matrix elements of A would be A super mu sub nu. However, what I wrote as matrix elements is the line above, A sub mu super nu. Look that they can be represented the same by linear operation, as you can tell, but I just was inconsistent between the matrix elements that I wrote and the representation of the components that I wrote afterwards in terms of index notation. While this is pretty relevant for what I'm going to talk about, I think it's important to state the inconsistency between the matrix product that I wrote and the index notation representation that I wrote so that it doesn't throw anybody off. This inconsistency can actually be helpful to show that the choice to represent vectors as rows or column vectors is completely arbitrary, how we represent them. For example, in the example below, I chose to represent the elements of the vector space V as column vectors and the elements of the dual as row vectors, whereas in what is written above, in the line above, then I represented the elements of the vector space as row vectors and the elements of the dual as column vectors. So you can tell this is a choice. I hope that this little inconsistency in the way I wrote at least serves us to illustrate that notion. Okay, that said, just keep that in mind. I'm going to be using from now on the one on the line above. So when you look at the board, just assume that what is written in there is the matrix product on the line above. The matrix product on the line below is the one that actually stays on the board, but is the one that should be mentally swapped by the correct one. My apologies, and let's go back to it.
And A mu nu acts on, so let's see, the components, right? You can contract these two indices with, to get a real number, to get no indices, which is what a number would have, I have to get A mu and get V mu, contracting it with elements of V, and an omega nu. So as you can see, this matrix takes one element of the vector space V, one element of the dual space V star, and returns this a real number. There's no indices here, it's just a sum of numbers that gives you a real number. So this object has two indices, and one is covariant and one is contravariant. So we call this A is a one type tensor, which means one time covariant, one time contravariant. All right, and consistently, it's got one covariant index mu that is contracted with contravariant vectors V, and one contravariant index 2 that is contracted with covariant indices from the covectors omega. All right. Now, how do they transform under change of basis? Well, they transform with lambda per covariant index and with lambda tilde per contravariant index. So if I do a change of basis and I compute A prime in the different bases, let's call this, I don't know, mu nu, that's gonna be. So I'm gonna have an A here, that is I'm gonna call sigma rho, for example. So I need, for the sigma, which is covariant, I need a lambda. All right, so I need to transform it into a mu, one lambda, and then one lambda tilde, that is going to contract the rho. So that's going to have a nu and then a rho here. So you see, that is how A transform, oh, tilde, I didn't write the tilde, my bad. Okay. That is how A transforms under change of basis. Once with lambda tilde. Now, interestingly, you've seen that in linear algebra. Let's try to write this as a matrix product, shall we? What kind of matrix product is this? Well, I can reorder this. This is the same as writing lambda mu sigma A sigma rho lambda tilde nu rho, right? Okay. But what was lambda tilde? Now, it's looking like a matrix product, right? But what is lambda tilde? Remember, the lambda tilde is the inverse transpose of lambda. So I can do lambda mu sigma A sigma rho, and then I write here inverse transpose. So I take the inverse and change the indices. Lambda in -1, and I change the index for the transpose now. Rho nu. And now it's written as a matrix product. Do you remember your algebra with your change of basis? Only that you call it, if this is a matrix product, this is lambda times A times lambda -1. You see? And this is, well, it's the transpose, right? But it's multiplying from the right, exactly the same thing. That's why the transpose acts. Only that in linear algebra, you call it probably P. PAP -1. That's probably what they call it, because that's what they call it in linear algebra. In differential geometry, like in the adult version of linear algebra, we usually call them lambda. All right? Okay, so you've seen this is the change of basis for a matrix. But now you know that it's not for a matrix, really. It's for an object that is once covariant and once contravariant. Because there are other objects that I can represent as matrices. Imagine that I have something like this, B mu nu, something with two indices downstairs. That I can also represent as a matrix, but that thing acts only on vectors. So that thing takes a vector V mu and another vector W nu and returns a real number. So this is an object that is twice covariant. It's a type 2-0 tensor. It's twice covariant and still will be represented as a matrix. And this is where things can get confusing if you rely too much in the intuition of row versus column. I take the opposite, right? Column versus row. To build intuition on that, because that's not it, okay? Now, if you remember, when you had quadratic forms and things like that, which are objects that are like this, in your algebra, I don't know if you saw quadratic forms, but if you did, probably you found out that it's actually a transpose here, instead of writing an inverse and things like that. Well, this thing will transform with two lambdas, not with lambda tilde, okay, if it's got two indices downstairs. All right. We will see more of that as we go. We're going to learn more stuff and what this actually means and what it is when we see differential geometry proper. But for an introduction, I think this is hopefully good enough. And I really want to invite questions for this. Now, we saw that tensors here, I mean, again, you can define tensors as, so let's write a definition for tensor, even though we will introduce tensors properly as we go in the course. But let's write a definition with what we know. All right, so we can define a type RS tensor, which by type I mean R times contravariant. The first number is contravariant, the number of times is contravariant. And S times covariant as a multilinear operator that maps R covectors, R elements of the dual space of V, and S vectors, S elements of the vector space V to a real number. Now, to understand with examples, tensor of type 1,0, which is 1 times contravariant. That's exactly a vector. Vectors are 1 times contravariant. Takes an element of the dual space and returns a real number. So in components, so the components have one is 1 times, look at the pattern of the logic. 1 time contravariant, 1 index upstairs. like a vector, like the components of a vector, right? And indeed, it contracts, oh, this is a mistake. It contracts with an element of the dual basis, omega, and it returns as a real number, the sum of components, right? Multiply. So a type 1, 0 tensor is a one-time contravariance. That's what we call a vector. Now let's look at the 0, 1 type. The 0, 1 type is 1 times covariant. That's exactly an element of the dual space. So it has an index downstairs, covariant index downstairs, right? Acting on a vector, remember the row acting on the column, same kind of thing. So acting on a vector, this thing returns a real number. This is a tensor that is one-time covariant. This is what we call a covector in physics. Now, we can have a tensor that is one-time covariant, one-time contravariant, and type 1, 1 tensor. Then that is like a matrix in a way. You can think of it as taking one column and one row, just to think a little bit about representations. Don't take it literally, right? And then takes one element of the vector space V, one element of the dual space V star, and contracts with both of them and returns a real number. Now, of course, you can have a 0, 2 tensor, which is a twice covariant, so two indices downstairs, and that thing takes two vectors in V and returns a real number like that. This thing is also a real number, of course. Now, this is the misleading thing if you think of rows and columns. This thing you can represent as a matrix 2 by 2. This thing you can represent as a matrix 2 by 2. Also, if I have a 2, 1, a type 2, 1, sorry, 2, 0, that I can also represent as a matrix. Okay, so thinking of columns as contravariant and rows as covariant or something like that is really not helpful long term. It may help understand a little bit how these operators work, but it's not the core of the thing. That's related with how you represent them. Okay. Now, of course, you can have bigger monsters, right? You can have a 1, 3 tensor. So what is that thing? That thing will have components. All right, so it's one times contravariant. So it's got 1 upstairs and then 3 downstairs. So sigma nu rho. And that thing would take what? It would take one element of the dual space, omega, and then 3 elements. So I need another one here. Let's call it, I don't know, Z. Why not? This takes a V, a W, all of them vectors, and a Z, all right? And that is equal to T mu sigma nu rho, and that contracts with omega mu, with V sigma, with W nu, and with Z rho. And there's a real number. So you see this thing has 4 indices. One of them, the first one, is contravariant, and the other 3 are covariant. Okay, so that's important to keep. Never write it below. Important. Never write it below the indices. You need to respect the position. This is the first one. This is the second one. Third and fourth. Okay. All right. So this is a tensor in general, and a tensor is just a linear operator that takes copies of the space and its dual and returns real numbers. Now, if you ask, okay, how does this object transform on the change of basis? Let's say the 1, 3 tensor. Well, it's easy. It's 1 lambda per covariant index and 1 lambda tilde per contravariant index.
So as you can see, you can tell in the first line that I have 1 lambda tilde that is changing basis for the index, for the superindex mu on the left, contracting with a superindex alpha that is at the very rightmost, right? And then you see 1 lambda tilde for the contravariant index, and then 3 lambdas for the 3 covariant indices. Now the second line is actually the same as the first line. The only difference is that we used a little trick. I personally call it the trick perch, and that's because my student Thales Rick Perch, whose email is trickperch at uwaterloo.ca, likes to use it a lot. That's one of the TAs of the course. You'll get to know him. Anyway, the trick is convenient because basically consists of, for the T prime, when we have transformed the tensor to the prime basis, if you want, just use prime indices. That allows you to use, as you can see there, the same indices in the change of basis, only with primes. It's easier to remember and more difficult to make mistakes with the characters, with the letters, with the indices that you use. I will probably use more the first one, but I wanted to let you know because it's pretty useful. Now let's go back to the main video and let's discuss a little bit the notion of a metric. Although just an introduction, but a little bit to have a little bit of an idea of what a metric is.
Right. Consider that we have a non-singular symmetric type 02 tensor, so a twice covariant tensor G of components, of course, twice covariant, G mu nu, and we consider its matrix inverse, G minus 1, of component G super mu nu, so that they satisfy, by that I mean the tensor that satisfies, the tensor that is twice contravariant, that satisfies that the matrix product of the two gives you the identity, so the matrix inverse, that's what I said. So we can use now that tensor to relate every element of the vector space V with an element of its dual. How? Well, I define, so for, if I have a vector V, of course, in the space V, such that V I write in a basis like V mu, E mu, right? Then I can associate an element of V star. Let's call it, I don't know, V, or maybe I can call it like, I don't know, V tilde, why not? V tilde, that is gonna be V mu, V tilde mu, E mu, such that V tilde mu, it's equal to G mu nu, V nu, and that's the definition. So I associate, for every element of V of components V nu, I can associate an element of V star of components V tilde mu, that is contracting it with the metric. Okay, the metric acting on the vector returns a vector with an index down. And what we do when we do that, what we say is like, well, let's drop the tilde and say that this thing is the covariant version of the contravariant V nu. So the metric allows us to establish an isomorphism between the vector space V and its dual V star. And that isomorphism tells you, well, for every vector V, let's associate one element of the dual, one covector V sub mu, if you want, for the components, such that is related with the metric like this. Now, this is super important because in a way it's saying, yeah, these two things are kind of the same object, kind of representing the same object, one with the index up, one with the index down, we say. So because of that, we say that the metric lowers the index of V. Now, the same way, you can say, again, this is a bit hand-wavy as it is in terms of definitions, but we will see it way more in depth, trust me, when we see properly differential geometry. Now, same way, you can use the inverse to do the opposite, right? You can have G mu nu and then V nu. Right? You can lower and raise indices with the metric. So in a sense, you're establishing, it's like in quantum, right? When you say in quantum, I can have the vector psi, and I can have the ket psi, and then the bra psi. And this bra psi is not any bra. It's the one that corresponds to this one, right? And how do you compute it? Well, I take the Hermitian conjugate and so on. Well, it's kind of that. That's what I'm doing here. I'm saying, if there's no metric, and this is something they don't tell you in quantum, usually, if there's no metric, I have no way to, for every vector, for every ket psi, I can build a bra psi. You can't unless you have a metric. When you have a metric, you are associating every vector psi, every ket psi with a bra psi. Only that the metric that you use in quantum tends to be the identity. Of course, if this is the identity, then yeah, trivially, the numbers are the same. It's like, oh yeah, for every column I have a row, right? Well, in general, this G mu nu will not be the identity, all right? And when we start seeing differential geometry and curved manifolds, curved spaces, and so on, we'll see that this is not the identity. But of course, this will allow you to define norms, distances, and inner products. As in, like, I can say, right, I can talk about the norm of the vector V as take G mu nu and contract it with V twice. And I define that as the norm square of V. I can do that. And if it's the identity, it's just the square. The square of the norm is the square of the components summed, right? Although this G mu nu again only needs to be non-singular and symmetric. Doesn't have to be the identity. And we will discuss why, right? Because if we talk about norms and we talk about distances, we want it to be symmetric. I want the distance between you and me to be the same as between me and you. And we will discuss why and so on and where it comes from later on. But I want you to understand that we can use a metric to lower and raise indices. And the reason why usually this is not introduced in your calculus courses, in your quantum courses, is because you are in the simplest case where the metric is the identity. Now you see why oftentimes people tell you, and then you have E mu, I mu, A mu, and that's an Einstein sum. No, it's not. To be an Einstein sum, it has to be like that. But what they're using, well, if the metric is the identity, then lower the index. I do my multiplying by the identity, and the entries are the same, and that's an Einstein sum. That's the abuse they usually do. We cannot do that abuse because our metrics are not, even in the simplest case, in special relativity, our metrics are not going to be the identity. And therefore, indices up or down matter, and we need to lower and raise indices with the metric when we need it. This may be a bit confusing. Please do ask questions when we have the live sessions, but this will get explained properly when we actually see the proper math in the block about differential geometry. All right. So the one thing I want to tell you, something interesting, is that I can lower and raise indices for any tensor. If I have a tensor t mu nu, I can lower the index by multiplying. For example, I can get t sub mu by multiplying twice by the metric, right? G mu nu, no mu, well mu, yeah, mu sigma, g nu rho, t sigma rho, for example. As you can tell, this one lowers the rho to a mu, and this one lowers the sigma to a mu. And these two tensors in principle are very different. This is a twice contravariant thing, this is a twice covariant thing, but if we have a metric, we can relate the two. Finally, realize the following. We can also raise one index of the metric. So this is the metric with the two indices down. This is the metric with the two indices up, which is the inverse, right? But what is the metric with one index down and one index up? Well, let's raise and lower. So I want to find G mu nu. So I need to raise, I get one mu alpha, G alpha nu, and that would be this, right? That raises the alpha to a mu. However, this thing, you may recognize already, because this thing is the same as this thing. So this is the delta. This thing is the delta mu nu. So indeed, the delta mu nu, the identity, is the metric when it is one time covariant, one time contravariant. So the metric lowering one index and keeping the other one down is actually the identity. And that's true no matter the curve space that you're considering, no matter what metric you consider. And it's also true even if it's non-Riemannian, if the signature is different from positive, right? This is true. This is also true for relativity, let's put it like that, for when we see that. Anyway, I threw at you a lot of stuff with this. Keep in mind that the objective of this is not to understand the objects that we have here. We will understand them, and trust me, we will understand them properly when we see differential geometry. But this, I hope, will give you some crash course on practicing index notation and on understanding what is meant by the notation and a little bit of the mathematical structures that are behind. We will see more of this as we go, and I promise that we will understand it. Now, make sure that you know how to handle these things in terms of user level and being able to lower and raise indices and understanding what it is and manages index notation. I will upload practice sheets of index notation for you to practice a little bit. But other than that, I really want you to ask questions when we have the synchronous sessions. All right, and with this, we finish this two-part introduction, and we will begin with special relativity in the next sessions. Thank you.